All right, let's talk about 1.2 here. This is domain and range, and we're going to begin, as usual, with a definition. So, let's talk about the domain. So the domain is the set of valid x values, and the question that should come to mind when you read this is, okay, Mr. Bryant, that's a fantastic definition, I suppose, but what do you mean exactly by valid x values? So when we talk about valid x values, what we mean requires, well, another little note. So let's make another little note here. So a valid x value is a value that doesn't break the function. And you might say to yourself, okay, great. So the domain is apparently a set of valid x values. Awesome. And a valid x value is a value that doesn't break the function. So what do you mean exactly by break here? Well, that's going to require another sort of note. And let's look at that. So a value that breaks the function is either a negative under a square root or a division by zero. That's the two bad things. And if you remember, if you want a real output, that is, you want something in the range that is going to be real, then you're probably going to want to put in a, can't say that. So a value that breaks the function is either a negative under a square root or a division by zero. A negative under a square root isn't going to work as long as we're not allowing complex numbers in. And we're usually working with real values here, so that's going to result in a complex value out that isn't what we want right now. And obviously a division by zero is never going to work. Now there is a third thing, which is a non-positive number that is 0 or a negative number inside of a logarithm, but we'll get to that in chapter 4 when we get there. So basically, the domain is the set of valid x values. Valid x values are values that don't break the function, and a value that breaks the function is either a negative under a square root or a division by zero. That is, the domain, skipping over all this, the domain is the set of x values that don't result in one of these two situations, either a negative under a square root or a division by zero. So let's go ahead and take a look at finding the domain just using something really briefly. So let me set up an example here and we'll talk about it. So let's say in this first example that we're asked to find the domain of f of x equals x squared minus 4. So what this question is asking is find the set of valid x values that we can plug into this and it not break. So remember, we're going to look over our checklist, which right now only has 2 things on it, and we'll only have 2 things on it for most of this class. We need to look for negatives under square root. So, is there any number that I can plug in such that we will have a negative under a square root? In terms of real numbers, the answer is no. There's no square roots anywhere in here. Okay? And perhaps we should come over here and make a little note that what we actually mean by square root is an even root. Because this is also true for 4th roots and 6th roots and so on and so forth. But I don't see any fractional powers or square roots or 4th roots over here, so don't have to worry about this part. So a division by zero is the other thing to worry about, and there is no division. So we'll come down here and we'll write using this notation, which is my notation. We'll write then that the domain of f, okay, that's a d with a superscript, subscript f rather. So since neither of these conditions are met, we can come down here and write this capital D sub f, which is my notation for the domain of f, and we can say that, well, we can plug in anything we want to. It doesn't matter what we plug into this, we're going to get something out, so the domain is all real numbers. So we can do it one of 2 ways. We can either say that the domain of f is all real numbers, like that, or we can use something called interval notation, where we write it like this. The domain of f is every number on the entirety of the number line coming all the way from negative infinity to infinity. Please note that this is not an ordered pair. Infinity and negative infinity are concepts, not numbers. And we'll get more into this interval notation in a moment. But for now, you should just know that that's what this thing is called. This thing is written in something called interval notation. And we're going to learn exactly how it works. So, that's our first example, and we found the domain. So let's look at another example and see what we can figure out. So in this one, we're asked to find the domain of f of x equals 1 over x minus 1. So here's the process. Think of all the numbers, all the real numbers that we can plug into this, and which of these gives you one of these two situations. If it gives you either of these situations, then we need to just throw that out and the domain will be everything else. So there will be no negatives under square roots because I don't see any square roots anywhere in this problem, nor do I see fractional powers, nor do I see any even roots either. So since I don't see any of that, I don't have to worry about this first guy. So let's worry about a division by 0. Well, I do see a division. So the question is what number x do I plug in that is going to give me a 0 on the bottom? It is not 0. If you want to pause the video and try to figure that out, that would be a fantastic use of time. But the main thing that you need to look at is we want the bottom not to be 0. So we're going to come over here on the side in a slightly different color, and we're going to say that we want the bottom, which is x minus 1, okay, we want it to specifically not be 0. And then we're just going to solve this. So we add 1 to both sides, and we get that we want x to not be 1. This is what we want. I'll write that. We want x to not be equal to 1. Because if we plug in 1, we get 1 over 1 minus 1, and 1 minus 1 is 0, and that's bad. We just broke the whole machine. So the domain of f is going to be all real numbers but 1. So I'm just going to write that. All real numbers but 1. Now, you might notice that this is kind of a terrible way to write this. So maybe this interval notation is going to give us some better way to write this. And for that, I'm going to need to give you some more examples. So I'm going to go ahead and scroll down here, and we're going to see what we're able to do. First off, we're going to try to write all real numbers but x equals 1. That'll be our first example here. So if you think about the situation on a number line that we have here, here's the number 1, and we want everything but that. So how do we draw that? Well, we don't want 1, right? We want all real numbers but that. So we don't want to include 1, so we're going to put a circle on that. And you should remember this from your algebra days. The rest of it is we're just going to shade everything to the right and everything to the left. So let's go ahead and do that. So you get a situation that sort of looks like this, which is every number but 1. So how are we going to say something like that? Well, let's look at this. We want all real numbers but x equals 1. So we do not want to include 1. So here's the interval notation for this. We're going to say that our specific d sub f is going to be, our domain of f is going to be, okay, let's look at this. We're going to start down here at negative infinity, and we're going to go all the way up to 1. So we're going to start down at negative infinity. So we're going to open up a parentheses, and we're going to say negative infinity. And I'll explain what this means in literally the next step, comma, and we're going to go up to 1. Because we want to include all of these numbers here. Okay? Now, we do not want to include 1. 1 is not included on here with a circle. 1 is not included in here by saying all real numbers but that. And then if you go up a little bit, you'll see that we said x does not equal 1. In order to do that, what we say is don't include 1 looks like this. You put a parentheses. And that means do not include 1. But right now, all that we've said is all of this left part here is all that we've done. We haven't said anything about the right part here. So I'll show you how to do that separately over here. We still don't want to include 1. So we're going to put a parentheses. That's how we exclude something. Exclude something. So we're going to put a 1 right there. And then we're going to go up to how far? Well, forever. So infinity. And then we don't include infinity either. You cannot include negative infinity or positive infinity because you can never get to them to include them in the first place. This is that infinity plus 1 game that you probably played as a kid. So if you think you've got to infinity, you can always add 1 to it. You can never actually get to it, so we can never include it. Now, the domain is going to be all of these numbers together, both of them together. How do we do that? We use this thing called a set union, right like that. So this thing right here is called a set union. And this set union pastes intervals together. That's how you can think about it. So it just sort of joins them together at the hip, so to speak. So what this says go from negative infinity to infinity, but, and this is sort of the key, this is how I read this, skip 1. So this part here in the orange says skip 1. Okay? So we go up to 1. We do not include it because of the parentheses. And then we hop over, we still don't include it, and then we go on up to infinity. That's what this thing says. So if you want to say the domain of this function, 1 over x minus 1, it is this in interval notation. So let's look at another example, which might make things even more clear. So let's say we were asked to write all positive numbers, including 0, in interval notation. So first, let's draw a number line and illustrate that situation. So here's the number line with 0, and we want to include 0. So over here we wanted to exclude something. We didn't want to include it, so we put a circle. When you want to include something on a number line, you shade it in, and we want all the positive numbers. So that's the right part of this. So I'm just going to shade over that. And you get a situation sort of like this. Now, if you wanted to say this using, for example, an inequality, you would just say all of your x's greater than or equal to 0. And that's how you would say that. If you wanted to say this over here, by the way, you would just say x not equal to 1. If you wanted to say this using an inequality or an equality statement. So, how do we say this using interval notation? It's pretty easy. We just want to say that if the domain is all positive numbers including 0, then we're going to say that the domain of our function is just, we want to go from 0 to infinity. Okay? We can never include infinity, so it always gets a parentheses, but we want to include 0 this time. So over here, we wanted to not include, so we used a parentheses. Over here, we're going to use a bracket. And what this bracket means is that we want to include it. So, include it. There we go. So we want to include 0 in this. So this is all the numbers from 0 to infinity inclusive, if you want to say it using that sort of verbiage. So I want to take a look at your book for a moment. It has a very good table, figure 3 in section 1.2, that goes over this. And I want to just go ahead and prepare those of you sitting in a dark room trying to read this right now. This is going to blow your corneas out because it is a bright white. So just prepare for that. So this is sort of what we're talking about. So I've just got your book pulled up here and maximized for you. And it sets up your inequality, the interval notation for it, the graph on the number line, and a description using words. So you can say that they just picked a point A and B for some of these. And they said that if you want all x's strictly greater than A, we're going to go from A to infinity. And notice that we used a parentheses here, which means that we're not going to include A. This is what it looks like on a number line, and this is how you read it. X is less than A, you notice that we start with a smaller number, and negative infinity is smaller than all other numbers, so we go from left to right always. Here we went from A to infinity. Here we go from negative infinity up to A. We always start at the left. We always read to the right when we're doing these because this is mathematics. So negative infinity to A. We don't include A. We also don't include negative infinity. That's what this looks like. X greater than or equal to A, however, looks like this. Now, in the book, they've used the bracket instead of a dot, and they've used the parentheses instead of a circle. That's fine. You can do it either way. But this is x is greater than or equal to a, and the most important thing is, here's the interval notation for it. Okay, I'm going to scroll down a bit. Here is the notation for x less than or equal to a. We go from negative infinity, still can't include it, all the way up to a. We include a by using a square bracket. This is x is between a and b. X is between a and b, and here is how you do it in an interval notation. So you'll notice already that this is easier to write. So this is x is strictly between a and b. And we just say that we go from A and B. Notice that because of the parentheses, that means that we're not including either endpoint. And then it's got the rest of the permutations of this. It's got that we include A, but we don't include B. We include B, but we don't include A, and then we include both. So to include the point, you put a square bracket. To not include the point, you put a parentheses. And this is figure 3 here in your book, and it will show you everything that you need to know. It has all of the nice stuff over here for you. I highly recommend that you read this. If you need the link to it, it's in the Materials tab at the top of this lesson. So we're going to hop back over here and talk some more about these. And we're going to do, say, for example, another sort of example. So let's scroll down here, and let's see if we can't get a good, solid example of one of those, just to make sure that we know what we're talking about. So let's say that we're asked to find the domain of f of x equals the square root of x plus 4. So remember, the two things we have to look out for are x's that we can plug in such that we get a negative under a square root, or x's that we can plug in such that we divide by 0. There's no division in this problem, so we just have to worry about this square root here. Now, this could have been a 4th root or a 6th root or any even power root, and we'd still have the issue. Odd roots we don't care about. Even roots we do. So find the domain of f of x equals the square root of x plus 4. So what we want, what do we want? We want to make sure that this is not negative. So how are we going to set that up? Pretty simple, I say. Let's look at this and set this up. Let's say that we want x plus 4 to be not negative. That is, we want x plus 4, what's under here, to be greater than or equal to 0. As long as the entire thing, not just x, but the entire thing, the whole thing here, as long as this whole thing is greater than or equal to 0, we're fine. If it's 0 exactly, the square root of 0 is 0, it works. If it's bigger than 0, the whole thing that's plugged in, if it's bigger than 0, it's fine. The square root of a positive number is a positive number. If it's less than 0, we got a problem. So what we want is we want x plus 4 to be greater than or equal to 0. So we're just going to subtract 4 from both sides. That does not change the sign. And we're going to get that we want our x's to be greater than or equal to negative 4. So let me draw you a number line and show you what that looks like. So here's the situation. We've got negative 4. Here's your 0. And we want all of the numbers greater than or equal to negative 4. Well, if we want all numbers greater than or equal to negative 4, you can either put your bracket here, like your book does it, if you want to, or you could just put a solid dot on it, either one, and then I'm just going to shade everything up this way. And you get this sort of a situation. So how do you write this in interval notation is the question. Easy enough. Let's go ahead and write this in interval notation. Back in the purple that we did the original thing in, let's do the domain of f, because it was f. If this were a g, that would be a g, is equal to, we want all numbers bigger than negative 4, including negative 4. It'll look just like this. And this is the benefit of doing it the way that the book does. Instead of using the circles or dots, you just use the brace, and hey, you can see very clearly this is what this needs to look like. All right, so we're going to do one more example because I don't want to belabor this point too much. But we're going to come over here and look at one more of these things, and then we should be good to go on this sort of stuff. So let's find the domain of k of x equals the square root of x over x minus 1/2. So you'll notice that this is super bad because we have both a square root and a division. So we need to make sure of two things this time. So I'm going to split this in half, and we're going to do the top thing. We want this thing here, just like over here, we want the input of the square root function to be greater than 0. So I'm going to bring that down here, and I'm going to say that we want this to be greater than or equal to 0. And then we're going to solve this. It's already solved. So that's a condition that we want. because as long as we're greater than or equal to 0, plugging in here, we're fine. And then I need to make sure that the bottom is not 0. So I need to make sure that the bottom, x minus 1/2, does not equal 0. That's going to be the thing that I want. So I'm going to add 1/2 to both sides, and I'm going to make sure that the bottom does not equal positive 1/2. If you add 1/2 to both sides, 0 plus 1/2 is 1/2. So these are the two things that I need to make sure of. So when I come down here and write my domain, I need both of these conditions to be met. So let me come up here and look at it this way. If I wanted this half, which I'll do in orange, here's how I would write this. I would write this by saying I want all numbers greater than or equal to 0. So I want to include 0. So I'm going to include it like this, and then I'm going to go all the way up to infinity. Okay? And I want x not to be equal to 1/2. So I need to take this into consideration, but I also need x to not be 1/2. So you can pause the video for a second and figure out how to stitch those two things together, and I'll do it in just a moment. So let's take a look at this, and hopefully you were able to puzzle this out. But let's look at this and we're still going to start at 0. We're still going to start at 0. And we're going to go up to the number that we want to exclude. So we want to exclude 1/2. Okay, we want to exclude it, so we're going to use a parentheses, and then we need to hop and get the rest of it. So we're going to hop over 1/2. So we do it with this bit of text, and then we're going to go all the way up to this infinity. And that is the domain. So from 0 to 1/2, skip 1/2, that's what that means, go up to infinity. Okay? And as one last little thing here, I will actually draw for you the picture on a number line of sort of what we're doing, which might help out. So I'm going to scroll down a bit and do that. The picture that we're looking at. So it's this bit here, the 0 to infinity bit, but we also don't want to be including 1/2. So this is how you say that. We go from 0 to 1/2, we go from 0 to 1/2, then we sort of skip over 1/2 and we continue. So remember, this part here, which is not part of the answer, this box that I'm drawing is not part of the answer, but this is sort of how I think of how to skip it. So we're going to go from 0 to infinity normally. That's this part. But we want to skip 1/2, so we're going to do this. So 0 to infinity, but inside we're going to skip 1/2. We skip it with these guys here, these parentheses, and then we're just going to paste together these two intervals. So it's this interval here on the left, and then also this interval here on the right, and in both of them we do not use the 1/2. So that should get over the main part of what this is trying to talk about. And now we're going to move on to the next concept. So let's say that you have an example, a problem that asks you this. Find the domain in the function, and then it's a set of ordered pairs in which the x's don't repeat, which is the definition of a function. So this might not look like a function to you. You're expecting f of x equals something, but this is indeed a function where your x's don't repeat. 7, 2, 4. That's probably the first thing you should check. And it asks you to find the domain. Okay, well the domain is going to be a set. So if we call this function f, then our domain of f, I'm going to let you see if you can figure it out. I'll give you a hint. It is indeed a set. Okay, so the domain is just going to be the set of particular x values. So the domain is going to be 7, 2, 4. Sets don't care about order, though it is generally advisable, at least, for you to put these in order. So would I prefer you to write this 2, 4, 7? Yeah, sure. But if you wrote it 7, 2, 4, that would be the order that I would be looking for it as well. That should be pretty easy to figure out, but it's just the input values. So these input values are the domain, and that's it. Which brings us to our definition of range, which is the other part of this puzzle. So let's talk about that now. So the range is the set of output values of a function given valid inputs. So I'm going to draw this picture again and just remind you of what I'm talking about. So you have your domain over here, and it's full of all sorts of numbers or whatever it is. And your domain is basically, you've went through and you've filtered out all the stuff that's going to break your function f, And then your range is sort of like the holding area for all of the outputs. So your domain is all the things that are going to be able to go into this function machine, and then your range is all the things that come out of it. So for example, if your function machine were a machine that made Twinkies, you wouldn't want screws to be in your domain. The valid domain of a Twinkie function would be the cream filling and the bread exterior. Those would be the only two things in your domain, and your range would be Twinkies, the outputs. What would not go in here would be screws, for example. You wouldn't want screws in your Twinkie. So the main thing that you look out for is your domain is just a set of valid inputs. So what we're saying is the range is the set of outputs, this thing over here in green, given that we put valid things in the first place. Well, valid inputs are called the domain. So that's all that we're doing. We take things out of here, we run them through the function machine, and they get turned into something else. As long as what we're plugging in, as long as we ensure that what we're plugging in, that is elements of the domain, are valid, that is they're not going to break anything, then we're guaranteed to have a range that works. And that's all that this is talking about this entire time. So let's talk about set builder notation here. And set builder notation is just a method of telling you a set of elements that satisfy a certain condition. So it's going to look like, well, in general, this. It's going to be the set of numbers, x or y or whatever your variable is, such that, this thing right here means such that, some statement about x is true. So whatever your statement about x is. Okay. So here's what we're talking about. So let's give an example. Let's say the set of x, let's give an example here. So let's say that this is the set of numbers x such that x is in the natural numbers, and x is even. So if I wanted to actually write out what this set would look like, it would look like this. So the natural numbers start with 1, but we only want even numbers. So this would be 2, 4, 6, 8, so on and so forth. The power of set builder notation is that you can build some very complicated sets using almost plain text English. So this is read, the set of numbers x, this still means such that x is an element of the natural numbers, and we've seen this before, and x is even. So this is going to equal the set containing 2, 4, 6, 8, so on and so forth. It's only containing these natural numbers because we said that part, and it's only containing the even ones because we said so. That's basically all of set builder notation, and we're going to use it more and more as we progress throughout the year, so you will get better with it. But the absolute last thing that I want to talk to you guys about is the concept of a piecewise function. So let's talk about a piecewise function. So let's say that we're given this function. We are asked to graph f of x equals, and this is a piecewise defined function, so it's in two pieces. This function is equal to exactly 4 if x is less than or equal to 1, and it's equal to x if x is greater than or equal to 1. And we're going to evaluate some stuff using this function in a second, but first, we were asked to graph it. So let's get our x and our y-axis here, and let's graph these functions. So clearly, 1 is where this thing changes. So as long as we're less than or equal to 1, that is, we're down here on this negative part, it's just the constant function 4. So let's go get 1, and let's put it here. So here's 1. Okay. And it is the constant function 4 as long as we're less than or equal to this. So the constant function 4 looks like you go up here to 4. And since this is the output, it's to the right of the equal sign, this is the output. What we're going to have here is that we are always at a height of 4 as long as what we plugged in was less than or equal to 1. So for all the numbers from negative infinity all the way up to 1, all that we're doing is getting this, we're getting this here line that I'll do in green. So it's just going to be this line, which is straight, all the way forever, up until 1. So up until about right there. So no matter, as long as you're less than 1, so anything down here, you're just going to hop up to a height of 4. That's the output. That's in the range, is 4. As long as you're up here. And then at 1 equals to 1, it's also 4, so we're going to put a dot. Okay? And then for every other x bigger than 1, it's just going to be equal to the function x. That is the line with slope 1 and y-intercept at the y-axis, because we didn't add anything to it. So this line has slope 1, so it's going to go up 1 over 1, up 1 over 1, up 1 over 1. And we need to know what that line is going to look like. Well, let me draw the part of the line that doesn't actually exist here in purple, and then we'll just erase it in a second. So let's imagine that the line probably looks something like this. Yeah? And it's just going to go on for forever. So beginning at 1, this is what the whole line looks like, by the way. It extends down through here. It's just x. It's this line. If you don't believe me, go on Desmos and look at f of x equals x. You'll see this very clearly. And this is just going to go on forever. All right? But it only exists, rather, if x is greater than 1. So think about drawing a horizontal line right here, which isn't actually part of the graph, but think about drawing it right here, and only to the right is this purple line going to exist. So I need to go back and actually erase part of it. So I'll go ahead and do that. So this is what the final version of this will look like, except at x equals 1, it's not x. So I'll put a circle right here. Okay. So the main thing that you want to look at is this is a graph of this piecewise function. That is, it is graphed in pieces. As long as we're less than or equal to 1, it is just the constant function 4. As soon as we get to 1, it becomes the function x. You'll notice that it's not continuous because it doesn't bump together. This is directly over top of this, and that's what it looks like. Let's say that we were asked to evaluate something in the next example, like, I don't know, something like f of 3, f of negative 7, and f of 1, let's say, for example. So let's look at each one of these. So f of 3, we're going to look at this 3 here, and we're going to say, okay, this is your x. Remember, this is your x. This is your input x. This is your input x. This is your input x. So x equals 3. You ask yourself a question. Is 3 less than or equal to 1, or is it greater than 1? It's greater than 1, clearly. So we're going to find f of 3 equals, well, 3. It's just whatever we plugged in. This is the function. As long as x is greater than 1, this is just the function f of x equals x. The identity function. It gives you back whatever you plugged in. So f of 3 is just 3. That's it. Plug in x, get out x, as long as x is greater than 1. Okay, negative 7. Negative 7 is clearly less than or equal to 1. So you plug in negative 7, and you're going to use this piece, because what you plugged in, the negative 7, was less than 1. What do you get out? It says you get out 4 no matter what. Okay, we get out 4 no matter what. And the last one is 1. We plug in 1. Which part do we use? Well, either 1 equals 1 or it doesn't. This is the one that has the equals included, so this is also just going to be 4. And that is how you evaluate these things. There's lots of practice for you guys on Delta Math with these sorts of things, and there are fantastic videos further explaining it if you need any additional help. If you need any additional help outside of that, you're more than welcome to ask me questions after you've played around with that. That being said, your book has a good definition of all of this, really breaks it down very well for you. There's more videos on Khan Academy, and then of course there's the videos included with Delta Math. So between all of us, you should be able to know this sort of stuff pretty well. But this has been an overview and a high-level view of all the sorts of stuff that you really need to know going into any kind of future assessment or math class. So with that, go ahead and get everything else done, and I'll see you back here when we start 1.3.